Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants. As you may know, Maths Aspirants is a collective of mathematics students across India initiated by myself in 2017, and we used to organize several online programs to help the students who prepare for different national level competitive examinations. As a part of that online problem solving session series, today we blessed to have Dr. Anindita Bhattacharya from Kolkata to handle a session on ordinary differential equations. Dr. Anindita did her BTech in aerospace engineering from IIT Kharagpur and then joined for Master of Technology MS at Department of Mathematics, ETH Zurich, Switzerland. And after that post-graduation, she did PhD from IIT Kharagpur and recently awarded PhD and now to join as a postdoc fellow at IIT Gandhinagar. I'm very thankful to Dr. Anindita for accepting our invitation and joining with us. I'm sure that today's session will be really very helpful to all of you. We are planning a series of sessions on ordinary differential equations. It's a very important topic in IIT JAM as well as CSER NET, GATE and other exams. So once again, I would like to thank Dr. Anindita for accepting our invitation and joining with us. I welcome everyone to this program. Welcome, Anindita.
Thank you, sir, for the kind intro. So today we will have a session on ordinary differential equations. So ordinary differential equations are differential equations of just one variable. So basically, if we have let's say a particle, and that particle is traversing a path, and that path is a function of just one variable, then that path can be described by an ordinary differential equation. So let us look into various kinds of ordinary differential equations and various methods of solving different kinds of ordinary differential equations. So first, let us look into first order ODEs. So what are the methods? Separable, linear, exactness, Bernoulli's. Key focus would be on Lipschitz conditions for existence or uniqueness. So what are separable equations? So standard form is dy dx equals to g as a function of x, h as a function of y. So we can see the right hand side can consists of two functions, g and h. One is a function of x and the other is a function of y, and they can be clearly separated. So we can bring this hy into the left hand side. So it will be 1 over hy dy equals to gx dx. Then we can integrate both sides, and just remember that on the right hand side there will be a constant c. So the key requirement is the ability to factor out the x part and the y part separately. So what are linear first order ODEs? The standard form is dy dx plus px, which is a function of x, times y equals to qx, which is another function of x. So how to solve this? So we look into something called an integrating factor. So let the integrating factor be mu x, and that will be exponential of integral px dx. So after we calculate this integral factor, integrating factor, or IF, so we multiply the entire equation by mu x. So mu x dy dx plus mu x pxy equals to mu x qx. So the simplification is, so if we now integrate this, it's an easy simplification. It is ddx of y times mu x, which is nothing but the right hand side is mu x times qx. And so the final form is y times mu x is integration of mu x qx dx plus c. So then we look into exact equations. So exact equations are of the form m, which is a function of x, y dx plus n, which is again a function of both x and y, dy equals to 0. The exactness condition is del m del y is equals to del n del x. So if it is exact, there exists a function psi xy such that del psi del x is equals to m and del psi del y equals to n. So what are the steps? We integrate m with respect to x. Psi is equals to integration of m dx plus hy. Then differentiate with respect to y and equate it to n. So del psi del y would be equals to n. And then solve for hy. Fourth is the Bernoulli equation. Dy dx plus pxy equals to qx. This is the linear equation, which is times the right hand side is qx into y to the power n. N cannot be 0 or 1. If n is 0, then it is the linear equation. If n is equals to 1, then it can be solved by separation of variables. So what we do a transformation. We divide by y to the power n. So y to the power minus n dy dx plus px y to the power 1 minus n equals to qx. Then we substitute v equals to y to the power 1 minus n. The derivative becomes dv dx equals to 1 minus n y to the power minus n dy dx. The result is v prime plus 1 minus n pxv equals to 1 minus n qx. So this is a linear equation in V, and we can use the solution process of linear equation to solve this equation. So existence and uniqueness. So let the problem be dy dx equals to fxy, yx0 equals to y0. Existence, f continuous implies at least one solution. Uniqueness, the f must satisfy the Lipschitz condition. This fx y1 minus fx y2 should be less than L y1 minus y2. So practical check, if del f del y is continuous and bounded near the initial point x0 y0. Now let's look into second order linear ODEs. We look into some concepts like Wronskian, homogeneous versus non-homogeneous, methods of variation of parameters, undetermined coefficients, etc. So homogeneous versus non-homogeneous. Homogeneous is y double prime plus pxy prime plus qxy equals to 0. So if the right hand side is 0, it is homogeneous. If the right hand side is gx, it is non-homogeneous. The general solution is y homogeneous plus y particular. So y homogeneous is the complementary solution, yp is the particular solution to the non-homogeneous equation. The Wronskian, so if there are two functions y1 and y2, we take a determinant of y1, y2, y1 prime, y2 prime. If the Wronskian is not equal to 0 at any point in the domain, then the solutions are linearly independent. If they are 0 at all points, then they are linearly dependent. Undetermined coefficients. So undetermined coefficients is best for gx's polynomials, exponential, sine, cos, etc. Method is find the homogeneous solution, make an educated guess for the particular yp, then plug yp back into the ODE and solve for constants. If the guess for yp overlaps with the homogeneous solution, multiply by x or x squared. So variation of parameters. This works for any gx. So first find the solutions y1 and y2. Then assume y particular is u1, which is a function of x, times y1 plus u2, which is again a function of x, times y2. Then we will solve this system of these two equations. How do we get it? Let's look into it. So we calculate yp dash, and then we put in a constraint that the second parenthesis, the term in the second parenthesis is 0. Why? Because this orders higher order derivatives of u1 and u2. And then so the constraint equation is this u1 prime y1 plus u2 prime y2 equal to 0. And then when constraint is applied, differentiating again, we get this, and substituting all this back, and because y1 and y2 are homogeneous, we get u1 prime y1 plus u2 prime y2 equals to gx. Yes, going back to this, so we get this u1 prime y1 prime plus u2 prime y2 prime equal to gx. Then we integrate u1 prime and u2 prime to get u1 and u2. And then finally, the system of equations is solved by Cramer's rule. So you get u1 prime equal to minus y2 times gx by w, which is the Wronskian. u2 prime is similar. Okay. Now we look into system of linear ODEs. What is system of linear ODEs? Matrix form x prime equals to ax. X is a vector like this. A is a constant n cross n matrix. The solution is of the form xt equals to c1 e to the power lambda 1 t times v1 plus c2 e to the power lambda times t, lambda 2 times t times v2 plus dot dot dot. Lambda are eigenvalues and v are the eigenvectors. If lambda 1, lambda 2 is less than 0, it is a stable node. If lambda 1, lambda 2 is more than 0, it is an unstable node. If lambda 1 is more than 0, is more than lambda 2, it is a saddle point, which is always unstable. And if lambda 1 equals to lambda 2, it is an improper node. If lambda is real plus complex, like alpha plus minus I beta, if alpha is less than 0, it is a stable spiral. If if alpha is more than 0, it is an unstable spiral. If alpha equals to 0, it is the neutral stability. T equal to trace lambda 1 plus lambda 2. Determinant is lambda 1 times lambda 2. Characteristic equation is lambda square minus t lambda plus d equals to 0. If d is less than 0, it is unstable. If t is less than 0 and d more than 0, it is stable. If t more than 0 and d more than 0, it is unstable. Now we come to series solution. Ordinary points versus singular points and Frobenius methods for singular points. So classifying points, if we have an equation y prime prime plus px y prime plus qx y equals to 0, ordinary point px and qx are analytic at x naught. Singular point, either px or qx is not analytic at x naught. Classification of singular points, if limit of x minus x naught px is finite and limit x minus x naught square qx is finite, it is regular, otherwise it is irregular. Power series. So if y is summation of n equals to 0 to infinity an x minus x naught to the power n. So we substitute y prime, y double prime that is obtained from this into the ODE, shift indices to align powers of x, set the coefficients of each power of x to 0, and derive the recurrence relation to find an in terms of a0 and a1. What is the Frobenius method? If instead of x, we have y equals to x to the power r and then summation of similarly. So we follow a similar process and get the coefficients an for a given value of r and handle the indical roots r1 and r2. So roots r1 and r2 are distinct, not differing by an integer. The solution is given y1 equals to summation of an x to the power n plus r1, y2 equal to summation of bn x to the power n plus r2. If roots are equal, requires log n log x term. If roots differ by an integer, the solution may involve log x. Let us look at Laplace transforms. So Laplace transform of ft is fs, integral from 0 to infinity e to the power minus st ft dt. S is a complex parameter, sigma plus I omega. The region of convergence required for the integral to converge. There are key standard transformations that are available in any book. So if there's a first shift, if the function is multiplied by e to the power at, then we get f s minus a. If the function is signed with a k term and then multiplied by e to the power at, it is k by s minus a whole square plus k square. The second shift is if it is ut minus a ft minus a, then it is exponential minus ASFS, and Laplace transformations are used for handling piecewise discontinuous functions. The most important thing about Laplace transformation is the convolution theorem, which is f multiplied by g transformation is integral from 0 to t f tau g t minus tau d tau. So Laplace transformation of f times g is fs multiplied by gs. This is excellent for finding the inverse transforms when we have a product of two functions, crucial for solving Volterra integral equations. So solving initial value problems, we take the Laplace transformation of the whole ODE, then we substitute the initial condition, then we have a expression called ys equal to fs by gs, then we use partial fraction decomposition, and then take the inverse Laplace transformation. These are some derivative rules that help to find the initial conditions. Now let us look into some practice questions, easy practice questions. So dy dx equal to y to the power 1/3, y naught equals to 0. Is there a unique solution? Dy dx equals to y to the power 1/3, y naught equals to 0. Yes, so it is non-Lipschitz at y equals to 0. The partial derivative is undefined at the origin. So there are multiple solutions, y equals to 0 and y equals to 2x by 3 to the power 3 by 2. Moving on to the next question. What is the order or degree of this equation? Okay, so the solution is the order is 2, the highest derivative is second derivative, and the degree is 3, exponent of the second derivative. So next question is the Bernoulli equation substitution. So basically dy dx plus pxy is equals to qxy to the power n. How would you solve this problem?
Which equation?
Dy dx plus pxy equal to qxy to the power n. Like the process of solving this equation, how can this be transformed into a linear equation?
Okay.
So we divide as one participant has said, we divide by the highest power, which is y to the power n here, and then we substitute v equals to y to the power 1 by n. This is the substitution that we should do, and then it is immediately transformed into a linear equation in V. Next question, what is the integrating factor for this? This is very simple, but I have still included it. So I will, yes, it is exponential integral of px ds. Next question, what is the Wronskian for y1 equal to e to the power x, y2 equals to e to the power 2x? So yes, so it is the determinant of e to the power x, e to the power 2x, e to the power x, 2 e to the power 2x, which is the derivative. And so that gives you 2 e to the power 3x minus e to the power 3x, which should be equals to e to the power 3x. It is non-zero, so they are linearly independent. So what is the characteristic equation of this equation? Y double prime minus 4, y prime plus 4 equals to 0. So it is, yes, you can write it as with a whole square, r minus 2 whole square equals to 0, which is r equals to 2. It will be repeated. So the general solution is c1 plus c2x e to the power 2x. This form is because r equals to 2 is repeated. Next question, what is the exact condition for exact equation m dx plus n dy equals to 0? So the requirement is dm by dy is dn by dx. This ensures m and n are partials of the same potential function psi xy. Next question, Euler's method, dy by ds equals to x plus y. y0 equals to 1, the step is h equals to 0.1. What should be the what should be the value of y1? The answer is y1 equals to y0 plus h times f as a function of x0 and y0. That comes to 1.1. The next question is separability check. Dy dx equal to xy and dy dx equal to x plus y. Which one of these two equations can, or both or none, can we apply separation of variables? Xy is separable. So you can write 1 over y dy equals to x dx. X plus y is not separable as it cannot be factored as gx times hy. So what is the Laplace transform of y prime t? So it is Laplace transform of y prime is s times Laplace transform of y minus y0. So then let us look into this condition, this problem. Dy dx plus alpha y equals to 0. The initial condition is y at 0 equals to 1. So you can analyze, just analyze the property, solve this and analyze the properties for different values of alpha, which is a real parameter. Alpha is real. So just solve this equation, dy dx plus alpha y equals to 0. For the initial condition, y at 0 equals to 1. And let me know what you think of the nature of the solution. So you're correct. So we do this is nothing but a separation of variables. Dy over y equals to minus alpha dx. That gives log of mod of y equals to minus alpha x plus c1. Then we just take an exponential, y equal to c to the power minus alpha x. Then we apply y0 equals to 1. So 1 equals to c to the power e to the power 0, c times e to the power 0, which means c equals to 1. The result is yx equals to e to the power minus alpha x. This is the solution. So if y1 equals to 0, e to the power minus alpha should be equal to 0. No real alpha satisfies this. So y1 equal to 0 is not possible for any real alpha. Limit x to the power infinity, yx equals to 0, requires alpha greater than 0. y1 equals to 2, e to the power minus alpha equals to 2. So minus alpha equals to ln2, alpha equals to minus ln2. This is a unique alpha. Next question. X squared plus y squared equals to 2x plus 4y plus k. Find orthogonal trajectory passing through 2, 3. To the point 2, 3. So basically what we do is we differentiate. So we get 2x plus 2y, y prime equals to 2 plus 4y. Then we find dy dx, which is like y prime 2y minus 4 equals to 2 minus 2x, which is y prime 1 minus x divided by y minus 2. So then we do an orthogonal condition. So replace y prime with minus 1 by y prime. So the new ODE is minus 1 by y prime equals to 1 by x by y minus 2, which is y prime equals to y minus 2 divided by x minus 1. And so this is the new ODE and then you will just substitute in that it has to pass through the point 2, 3, and that should solve this and substitute that it should pass through the point 2, 3, and that should give you the value of the constant. So the trajectory will finally be y equals to x plus 1. Is it clear? Is it clear to everybody? So next, I go on to the next problem statement. Y double prime minus 2y prime plus y equals to e to the power x. The initial condition is y0 equals to 0, y prime 0 equals to minus half. Solve this.
Minus x by 2 into e to the power x.
Let me see the solution.
Is it the solution?
So what is your solution? Could you write it?
Yeah, the particular one using this IVP. Is it minus x by 2 into e to the power x? The
Minus
general
x by
solution,
minus x by 2 e to the power x.
yes, the particular one.
The particular
And this is-
solution.
you boundary conditions.
It is not minus, it is x squared e to the power x. Half x squared e to the power x.
Yes, correct, that's correct.
So let me show you the solution. So the homogeneous solution is r square minus 2r plus 1, which is nothing but r minus 1 whole square. So r equals to 1 repeated. So the homogeneous solution is c1 plus c2x e to the power x. The particular solution should be, the forcing function should be, is e to the power x. So we could guess a e to the power x and ax e to the power x are already in the standard solution. So the correct guess is a x squared e to the power x. Then we get y p dash, y double p dash, we substitute and we get 2a equals to 1, which means a equals to half. So the particular solution is half x squared e to the power x. So finally we have c1 e to the power x plus c2x e to the power x plus half x squared e to the power x. Then we apply y0 equals to 0. So this gives c1 equals to 0. And we put y prime 0 equals to minus half. So we calculate y prime x, and at y prime 0 it is minus half. So c2 is equals to minus half. And final solution is yx is minus half x e to the power x plus half x squared e to the power x. And we can sort of write it in a more aesthetically pleasing form like this. Is that clear to everyone? Okay, so moving on to the next question. So this is this doesn't have a y term, as you can see. It is second order linear ODE missing the y term. It is y double prime minus 2y prime divided by 1 minus x squared equals to 0. So we substitute v equals to y prime. So v prime equals to y double prime. So the ODE becomes v prime minus 2 by 1 minus x squared, v equals to 0. So dv dx equals to 2 by 1 minus x squared v. So separation of variables. Then we use partial fraction decomposition. Then we get this integral. And finally, after algebraic simplification, we get y prime equal to c2 times minus 1 plus 2, 1 minus x. And then we get y, final form is yx equals to a times x plus 2 ln 1 minus x plus b. Next problem, dy dx equals to y into y times 2 minus y. Y at 0 equals to alpha. Find yx and analyze behavior. Once again, the final solution is yx a times x plus 2 log 1 minus x plus b. Next problem, dy dx equal to y 2 minus y. Has anybody found a solution to this?
Ma'am, 2.
So your answer is 2?
Yes, ma'am.
Let me see. No, unfortunately not. So should I look into the, should I describe the solution?
Yes, ma'am.
Okay, so what you do is you do a separation of variables, dy over y, 2 minus y equals to dx, then partial fractions. So you get half or times y, 1 by y plus 1 by 2 minus y. Half times 1 by y plus 1 by 2 minus y dy equals to integration of dx. Then the simple integration, log of y minus log of 2 minus y equal to 2x plus c. So log y by 2 minus y is 2x plus c. Y by 2 minus y is k times e to the power 2x. Use y0 equals to alpha. So k equals to alpha by 2 minus alpha. And so the final solution, substitute k and arrange. Yx equals to 2 alpha e to the power 2x by 2 minus alpha plus alpha times e to the power 2x. This describes logistics growth. This is the logistics equation, and this describes logistics growth. So now we look into the qualitative analysis. So y equals to dy dx equals to 0 is y equals to 0 is unstable equilibrium. Y equals to 2 is stable equilibrium. At x tends to infinity, if alpha is more than 0, yx equals to 2. So if your answer yx should be 2 at x tends to infinity only, not everywhere. So it is correct if we are looking for the solution at x tends to infinity. Alpha less than 0, solution has finite time blow up. So next, let us look into a problem. Dy dx equals to y square minus 1 plus cos x, y0 equals to 0. What is the nature of the equation? This equation, dy dx equals to y square minus 1 plus cos x. I will write it. Do you want to try for some more time, or do you want to see the solution? Correct. So at origin, dy dx equals to, just substitute all the values and you will get equals to 0. So dy dx at origin is 0, implying critical point behavior. Near origin, dy dx is less than 0, since cos x is less than 1 for small x. So the conclusion is yx is strictly decreasing in the neighborhood of 0. The next equation, analyze the stability of this differential equation. Y double prime plus 2ay prime plus y equals to sine x at values of a equal to 0, 1 and 2. I will write this out for you. So at a equals to 0, it will be y double prime plus y equals to sine x. The solution is unbounded due to resonance, because y homogeneous and y particular solution will be similar. At a equals to 1, it is bounded. The e to the power minus x terms will vanish. And a equals to 2, the roots are real and it will have stable behavior. So solve this equation. X squared plus y squared dx minus 4xy dy equals to 0. So rewrite dy dx equals to, wait. Oh, I wrote plus 4xy. It should have been minus 4xy. Maybe your answers are correct. So just look into the process. I'm very sorry. I wrote plus 4xy. So write dy dx equals to this. Y equals to vx. So dy dx equal to v plus x dv dx. And then just solve it. I wrote plus 4xy instead of minus 4xy. If you wrote minus, maybe you would have gotten the correct solution. Periodic solutions, y prime double prime plus 4y equal to sine ax. What should be the value of a for the solution to be periodic? I will repeat. The equation is this is the equation. what should be the value of A for the solution to be periodic?
Excuse me, Anindita, you can explain, I think, because of the
Oh,
time.
okay, okay, sir. So the homogeneous solution is periodic with a period of pi. The particular solution sin AX is periodic with a period of 2 pi by A. The overall solution is periodic if the ratio of the periods is rational, that is, if A is rational. Then I have first order linear ODE, y prime plus x, 3x square y equals to x square. I can take this and you can solve it very quickly. I can share it here. Yes, you can, you can see this equation and solve it quickly and tell me the answer. Sir, should I end after this? I have a few more questions. We can share it later also.
Yeah, as the time is around 10, I think we can postpone that questions to the other next session.
Okay, sir. And so, sir, any feedback, sir?
Yeah, is the current problem over? Is the current problem is over? Hello?
Hello?
Yeah, Anindita, is the current discussion problem?
Oh, no,
is over?
I have just given the problem. I haven't received an answer. I can share the solution.
Okay, okay. Then you can complete that answer to that question, I think.
Okay, so the integrating factor is e to the power 3x squared dx, e to the power x cube. The solution when multiplied by e to the power x cube is this, and x to the power infinity gives us yx is equals to 1/3. So yes, the current problem is over.
Okay, thank you, Anindita Bhattacharya, for this nice session. I think, Anindita, you can turn off the presentation now.
Okay, sir.
So, dear participants, feel free to share your feedback or any comments regarding the session. All of you are encouraged to express your comments. You can turn on your video, unmute your mic, and express your views. Please.
Hello everyone.
Yes, Nikita?
Am I audible?
Yes, yes.
So I'm not turning on my video because of some network issues, but
So I can't hear you. Sorry. Can you say it a bit louder?
I'm not turning on my video because of some network issues here.
Okay, Nikita, it's no issue.
What did she say? I couldn't hear.
Yeah. Because of the network issue, she is not keeping the video on mode.
Okay.
Yes.
Ma'am, I just
Yeah, Nikita, yes.
Yes,
ma'am, I just want to say that your method of teaching was very efficient, and you explained all of the methods of solving problems very efficiently, and it was very concise, you know.
Thank you, Nikita.
So the steps were minimized, so we also had an interest in actually solving the question, and you know, you didn't complicate it very much. So,
Sir, what is she saying?
You didn't complicate the process of the solving of questions very much. It felt very easy when you explained it.
Okay, thank
that's what I
you.
was-
Yeah.
What did she say,
That's
sir?
Yeah, the method of explaining is very good.
Okay, sir. Thank you, sir.
So that's all I have to say, sir. Thank you.
Thank you, Nikita.
Thank you, Ajay. Thank you, Nikita.
Yeah, others also, if any of you How
Ma'am, the session was good and a lot of questions were discussed, and it was a good session. It was an interesting session as you gave the question and asked for solving it. So it was an appropriate good session, ma'am. So thank you for that.
Thank you, Brijesh.
Thank you, Brijesh.
Good evening, ma'am.
Thank you, Anne.
Am I
Yes,
audible?
Varada?
Yes, ma'am. Good evening, ma'am. My name is Varada. I have just completed my BSc, and this time I cleared JAM exam also.
Thank
So
you. Big congratulations, Varada.
thank you, ma'am. Thank you. So I actually lost touch with the subject of OD actually. So you helped me gain back that connection, I would say. And as somebody already told, like your explanation was like very good. Like you did not over explain things, and like it was very precise. So it was very
Thank you,
easy to
thank you.
understand as well.
Thank you,
So
Varada. Yeah.
thank you, sir, for organizing this class for
Thank
us.
Thank you, Varada.
Here, thank you, Indumati. Thank you, Srila. Thank you, Apsal. If I missed anybody.
Okay, thank you, Anindita. Let us wind up this session here. And yeah, hope that we can arrange more sessions from your side.
Okay, sir.